best example I can give you, this looks crazy. Sorry. Okay. The best example that I can give you of series circuits are, I'm sure many of you use string lights. Depending on when they were made, many of the older versions of string lights, you'll notice that, so like let's put some bulbs onto this thing. You can make them multicolor. Alright. You'll notice that when one of those bulbs burns out, they actually all burn out. Okay, so let's just say, here's our little voltage source. Okay. So here is a purple bulb, a blue bulb, a yellow bulb, gotta have a red bulb. I don't know. Orange, is that a thing? Maybe not. Let's go with this color. This is pretty. Okay, so light, 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 light. You'll notice with these string lights that it's usually all or nothing. So with string lights, when one of them burns out, when one bulb burns out, the entire light set ceases to light up. So let's say this nice yellow one over here stops working, then none of them are going to work. It's done. You're going to have to replace that bulb, get one that maybe hasn't burnt out. So these are usually connected in series, and what happens is when one bulb burns out, it acts as an open switch. Okay, it has the exact same effect as an open switch. Acts as an open switch. Well, why is it that that would affect all of these other bulbs? Well, the reason it affects them is because these are all in the same path. Okay, so the current is only traveling through one path in this circuit. In other words, we might have bulb number 1, bulb number 2, bulb number 3. I'm just going to make it 4. Bulb number 4. Okay, so here's a little circuit diagram of string lights. And so when I say that these string lights are connected in series, what I really mean is that these string lights only are allowing the current to take one singular path to travel through this circuit. So if one of these ceases to work, the current is no longer experiencing the potential difference that is provided by the battery, and that's crucial here. So characteristic of a series circuit, there is only one path for current to take. What that means, so that has an implication. What that means is that the current is the same everywhere in this circuit. Okay, so what this means is that the current is the same everywhere in a series circuit. are working properly, I will get the same reading. So if I know that the current here is 4 amperes, then if I throw an ammeter right over here, I'm still going to get a measurement of 4 amperes. So it's reading 4 amperes. If I put an ammeter over here, it's going to read 4 amperes. The current is the same everywhere in a series circuit, so that's really important. Okay. What is not going to be the same, though, is the voltage drop that happens at each successive point necessarily. In other words, if my total voltage here is 120 volts, and let's say across this first resistor, I'm not stepping just to lay it out similarly to how we did before, I'm not going to step down the entire 120 volts after the first resistor. It's going to happen incrementally. So if I climbed up 120 steps, I can't climb all the way back down and still travel the rest of this path. So what's going to really happen is I might step down here, let's say 30 steps or 30 volts. So let's say I step down here 30 volts. Well, how much is left from 120? I still have 90 steps left. Okay, so now I'm going to step down, let's say, another 30 steps across the next light bulb. Now that current is going to step another 30 steps across the third light bulb. So let's say 30 volts. But these are only the same because I'm assuming these light bulbs have the same resistance. Okay, so my point though is that if I step up 120 volts, I now have to step back down to 0 in increments, right? So this would bring me to 90 steps left. This would bring me to 60 steps left. This would bring me to 30 steps left. And this one would bring me from 30 to 0. Okay. So anyway, I just wanted to give you an overview. But the voltage drop across each of these will not be the same as our total voltage. And it won't always be the same from one resistor to the next. It depends on what the resistance of those resistors is. Okay, so now let's just talk about a parallel circuit. So if series circuits are characterized by only having one path for current to flow across, one path for current to flow across, then what do you imagine a parallel circuit would be characterized by? So a parallel circuit is actually characterized by the presence of junctions which allow for current to be split. So I'll show you one example of a parallel circuit. So parallel circuits are characterized by current being split across more than one path. See here is, here's our voltage source. We have 120 volts. We have 0 volts. But what you'll notice is once the current reaches this point, which we're going to call a junction, some of that current, wait, let me use a color you could actually see. So here's current total. Some of that current is going to go this first path, we'll call it I1, and the rest of that current is going to go this path, we'll call I2. So what is characteristic about parallel circuits is that your total current is being split in several directions. It will rejoin at this point here, and you will then have your I total back again as you reach the voltage source. But at these junctions, that current is being divided into two different paths. Okay. I'll go more in detail about parallel circuits when I'm actually going to teach them, but I want to start out by teaching series